If everybody would like to join me in welcoming Junsup Shim, who's giving our seminar today. Did his PhD at Seoul National University, then did his first postdoc at the Korean Institute for Advanced Study, and is now at Asia A in Taiwan. So he's here for a while. When do you leave again?
August 20th, I guess.
Okay, so yeah, he's here for a while, so if, there's plenty of opportunity to speak to him if you are interested. And he's working on here on cosmic fluidity. I think that's right, with Lee and others. But today he'll be talking to us about cosmic voids and their cluster counterparts. So go ahead.
Thank you for the introduction, Julian. So today I will talk about cosmic voids, which is not about cosmology, but it's more about large-scale structures. So in the first part of my talk, I will introduce a new concept of defining cosmic voids as the counterpart structures of massive galaxy clusters. And in the later part of my talk, I will demonstrate that we can actually identify them from a given data, be it dark matter or galaxy distribution. So this talk is based on these two papers, which were done with collaborators listed here. So let's get started from the observed distribution of galaxies. Here I'm showing you two-dimensional maps of galaxies, which were taken from a series of galaxy redshift surveys. And what you can immediately learn from these figures is that galaxies are not evenly distributed in space, but are aggregate to form a larger scale over densities in some locations. And at the same time, galaxies are evacuating from other locations to form underdensities. So this intricately connected pattern of over and under densities as a whole is called a cosmic web, which was first coined by Professor Dirk Bond in his seminal paper about 30 years ago. But today, I will not touch all the components of the cosmic web, but we'll focus on cosmic voids, and which I marked with dotted ovals in this dark matter distribution from the M-body simulation. So they are usually underdense structures, and as you can see, their size can range up to several tenths of megaparsec. So they are definitely the largest volume component in our universe. And these voids have been gaining more attention recently. The reason is because they can serve as a probe of various cosmological ingredients. For example, they can use for test the nature of dark energy, since voids are underdense structures, so they are matter deficient structures. In other words, they are relatively dark energy dominated structures, so one can test the nature of dark energy by looking at their shapes or size distributions. And on the other hand, you can also use these cosmic voids as the test tool for testing different modified gravity models, where we used to implement so-called screening mechanisms in order to reduce these modified gravity models to general relativity on small scale or in overdense environment. So when we test these models in these underdense regions like cosmic voids, then we expect to see some deviations from general relativity. So one can look at these signatures from the lensing signals, or one can use void galaxy cross correlations to constrain the linear growth rate of the structures. And last but not least, you can also extract some primordial information from these underdensities, which were shown to better preserve their initial position when you compare the location of the underdensities in the beginning, in the initial condition, and compare that to the late time density field. So because of these large applications in cosmological side, you can also do galaxy formation studies when you study the properties of galaxies which are residing in these voids, and you can compare these properties to those of galaxies in overdense regions. So you can both touch on the cosmological side and the structure formation side using these objects. So in response to these needs, there have been many different void finding techniques or algorithms have been and there was one interesting experiment. I guess, okay. So there was one interesting experiment showing how different the identified voids could be when adopting different void finding algorithms to the same given data, for example, dark matter or galaxy distribution. And as you can see in this figure, these green regions are all resulting voids identified by different void finding algorithms. And there is non-negligible difference from one void to another. And the reason for this diversity is that their different void finding algorithms has different assumptions on what voids should be. So this arbitrariness leaves some degree of freedom in determining the parameter values of the void identification methods. So there is some degree of arbitrariness in characterizing or defining cosmic voids from data. And what is even worse is that if you try to measure the basic statistics of the identified voids, for example, if you try to measure the size distribution of cosmic voids using the most sophisticated void finder these days, then the basic statistics from the measurement is very different from what is expected in theory, which is based on a spherical expansion model, which I will elaborate in a later slide. So on one hand, there is some technical diversity from the data side, and there is some gap between theory and the identified ones from the data. So these inconsistencies pose us a question whether we can define cosmic voids in a new way, while it's still theoretically motivated, but at the same time, we can consistently identify them from a given data. And the answer to this question is yes, we can have some.
Wait, 1 second. Peter says that we lost the audio on. Looks like can you online hear us?
Yeah, so for me, it's fine, the audio.
Oh. Yeah, I think it might be I think it might be some lag issue because it also said the internet was unstable. Oh, okay, Martin says, okay, well, let's just continue and it resolves itself. Sorry,
I guess I lost my connection to this link.
Yeah, I also lost my connection. Can people online hear us? Okay, well then, let's try again. Take two.
Okay. Yes, so the motivation of this work is to answer if we can find a new definition of cosmic voids that is theoretically motivated, but at the same time that can be identified from the data consistently. And of course, yes, this is why I'm giving this talk. So we can do so by focusing on duality or correspondence between cosmic void and cluster. And before I talk about what is duality or correspondence between these two objects, let's step back a little bit and talk about how cosmic structures form in general. So according to the standard structure formation scenario, we know that cosmic structures all form from the initial density fluctuations through gravitational instability. For example, massive galaxy clusters or massive dark matter halos are known to form at the high enough peaks of the initial density fluctuation, whereas cosmic voids will form around low enough density troughs of the initial density field. And if we want to describe the formation of these voids, that can be simplified to a spherical underdensity. So that is named as spherical expansion model, where void formation is approximated to an initial spherical underdensity. So I'm showing you concentric mass shells which compose initial underdensities and corresponding density profile at the bottom. So because these mass shells are in underdensities, they will expand because they are pulled by the surrounding relatively overdense regions. So the mass shells will become larger and the density well will become deeper. And since the inner mass shells usually experience or encloses more underdensities, so these inner mass shells has slightly higher expansion rate, which means they will gradually catch over the neighboring outer shells. And at some point, all of the shells will pile up at some radius in some time. So this is the moment where we call shell crossing. And this is the onset where the formation of void is completed. And based on this picture, we have some characteristic feature when the formation of void is completed. So as you can see, we have some matter concentration around these circle, which is the resulting a layers of concentric shells. So we do expect to have some mass boundary around voids, and we expect to have inverted top hat like density profile with average density contrast to be minus 0.8, which is about 20% of the cosmic mean. So this is the very simple expectation what we can get from this spherical expansion. Then what we can, now we're ready to talk about this duality or correspondence between void and cluster. So suppose we have a universe whose initial density fluctuation looks like this, and let's name this universe as mirror universe. Then we will have massive clusters around the peaks of this initial condition. Now, if you imagine another universe, I guess I'm again freeze. Yeah, so it takes some time. So if you imagine another universe with exactly the sign opposite version of the initial fluctuation, then these initial peaks of the density field in the mirror universe now becomes initial density trough in the reference universe, meaning that the locations where we used to have massive clusters will now be the formation sites for cosmic voids. So in this picture, one can always associate a void in the reference universe to a cluster in the mirror universe. And one good thing about this identification is that we don't need to worry about determining the parameter values in this dark matter distribution, but we only need to define or identify gravitationally bound object in the other universe, which is in practice more easier to identify them from a given galaxy or a dark matter distribution. So the following question is that, does these cluster counterpart regions or cluster counterpart structures do actually behave like cosmic voids? So we, to test this idea, we utilize a pair of simulations whose initial density fluctuations are designed to have exactly the sign opposite shape as given here. So I'm showing you a schematic diagram of our simulation setup with some dark matter particles. So using the same initial matter power spectrum, we displace particles in a kind of very crudely speaking in an opposite way to generate initial overdensities in one simulation and initial underdensities in the other simulation. So I'm just showing you very small patch of the whole simulation box. And we let them evolve under gravity as we usually do. Then the way how we define cosmic voids or cluster counterpart structures in the reference simulation is starting from first defining or identifying massive clusters in the other simulation. So from the dark matter particle distribution, for example, we apply a friends of friends algorithm to first identify these gravitationally bound objects, and then trace these particles to their initial stage and look for their corresponding particle distribution in the other simulation. And then again, trace them forward in time. And then we consider these particles represents or delineates the boundary or the region of cosmic voids. So we will now call these dark matter particles as void particles because these will be the member particles of this cosmic structures. And this is the resulting initial density field from our simulation setup. So I'm showing you the same region in two different simulations. And I colored with red and blue, which red is representing overdensities and blue for underdensities. So if you look at the whole morphology, it's exactly the same. But the color or the amplitude of the field is inverted. So for example, if you look at these dark blue dots, which is underdense structure, now becomes overdense structures in the other simulation in red. So this is the simulation specifics. Then we can also draw a map of dark matter particle at redshift 0. And again, I'm showing you the same region in the mirror simulation and the reference simulation. And here I mark the member particles of the 8 most massive dark matter halos in this region with different colors, and the corresponding particle distribution in the reference simulation. So as you can see, the particles that compose this massive dark matter halo, which were compactly located in small region, now occupies a very large space, which means they are actually large voluminous structure, meaning that they are underdense structures. And now if you recall our theoretical model in the beginning, the expectation around the boundary was we were supposed to have some concentric shells of mass. And if you look closer to these colored regions, there is some small mass clumps which were pushed away from the center of these voids and to the boundary of these regions. So although the shape doesn't look circular or spherical, but the qualitative distribution of mass is consistent with the theoretical prediction. Now we want to quantitatively measure some properties of these regions. So we need to define the volume of these cosmic voids. So we pixelate the whole simulation box into smaller cubes, and then determine the identity of these volume elements according to the nearest particle to the center of these boxes. So for example, we can categorize these regions as void volume elements, since the closest particle to each of these boxes is a green particle, which is void particles. Otherwise, we categorize as non-void volume element, which means they don't belong to any of the voids in our set. Then you can, again, show the spatial extent and the distribution of these cluster counterpart structures. And the color represents the mass range of the dark matter halos or clusters in the mirror simulation, which were used to identify these structures in the reference simulation. And we restricted our halo mass ranges to be above 10 to the 13 H inverse solar mass. And this is why we specify these structures as cluster counterpart voids. And as you can see, there are many more yellowish small patches than blue or purple patches, which is simply reflecting the fact that we have much more smaller mass halos and than the larger mass halos. So this is just simply doing one-to-one correspondence between halos and voids. So now I will show you the properties of these cluster counterpart voids. And the first, the most interesting feature of this void identification is the tight correlation between the size of cluster counterpart void and the mass of the corresponding clusters. Here I'm showing you the mass range of the halos in the mirror simulation on your x-axis, and I'm giving you effective radius of cluster counterpart void in the reference simulation on y-axis. And the key message here is that a cluster counterpart void that is corresponding to halos of greater mass typically has larger radius. In other words, if you happen to identify a cluster counterpart void of a particular radius, say like 20 inch inverse megaparsec, then that is statistically comparable structure to the halos of mass 10 to the 15 solar H inverse solar mass. So in this picture, you can always associate a particular size void to a particular mass halos.
So can I ask something about that?
Yes.
Yeah, like, so how was this RV measured, like, or defined?
Oh, yes. Oh, sorry. So this RV is effective radius, which is the radius of the sphere whose volume is identical to the volume of these cluster counterpart voids.
Wait, say it again. Is the radius of the sphere?
Yeah, whose volume is identical to the volume of the void. So you can just, you just calculate as the voids are, as if the voids were a sphere.
I see. But the void volume, though, is measured in the Eulerian real space. Like,
Yes.
Okay, I see. So if you go back, to your plot, showing the comparison between the two simulations, I was just puzzled about something. Yeah, so this one, like, so if I look at, like the red or the green voids, right?
Yes.
Right, right. So they sit in these empty regions, but they don't seem to really correspond to what I would have called a void at those locations, right? Because there's like much more empty space around them, right?
Mm-hmm.
Yeah, so right. So when you measure this void volume, like, are you just using, for example, just those red points, or using the whole empty region around those red points?
So these red points are actually dark matter particles, and you assign volume elements, which I describe in the later slide here. So depending on the location of the particle, we can assign volume elements to these particles. So we don't have any spatial overlap between different voids, but we can always assign these volume elements to only one of the void in our setup.
But Neil's worried about you missing a lot of apparent looking void space. Like go back to your.
Oh yeah, okay. So if that's your concern, then yes. So I just told you that I'm just displaying like the 8 most massive dark matter halos. So if you lower the mass ranges and then you identify smaller mass halos, then they will all fill up the spaces in between. So eventually, if you do not restrict yourself to masses of a 10 to the 13, and then you lower the mass, lower mass limit, then you will eventually fill all the gaps which are colored in white. So that's.
We'll go back to your plot again, and there's various. So right there, like that red one, it looks like you're only covering the lower half of what most people would call void, right? The upper part is traced out.
Yeah.
That dark stuff.
Yeah.
And you're saying that upper part's gonna be filled in by lower mass halos.
Yes. Or
lower volume.
yes, maybe lower than these masses.
Right.
Yeah.
The other thing is that the triangles are offset from the circles.
Mm-hmm.
Are those circles the same ones in the left-hand plot, or they're?
Yes, the circle is the position of these center of these particles. Yeah. So there is definitely the difference between the two, which you go back to our introduction. So when you do some investigation in terms of their initial position to later time position, underdensities are known to stay at their initial position. So I would probably say this is the initial position of the underdensities in the beginning, but the overdensity ones has been moved by the tidal interaction. So second quantitative measurement will be density profile. And I'm now showing you 2 different types of density profiles depending on whether we only include void volume elements or including all volume elements. Since we're showing you spherically average density profile, it matters because as you said, if we only include the volume elements that only belongs to voids, it will have some different density measurements. So on your left plot, I'm showing you 5 different categories which are categorized by their corresponding cluster mass. So we're spanning 2 orders of magnitude in mass. But the important feature from this density profile is that we have very universal density profile even at different redshift within these cluster counterpart voids. And this trend still remains even if we include all the volume elements around the center of these voids. We still have very similar density profile, although the outer part of the density profile now turns down because we're including non-void volume elements. And then again, if you recall the theoretical prediction based on spherical expansion model, where we expect to have inverted top hat-like density profile because all the masses are piling up at some radius, then we can crudely say there is that kind of feature in our measured density profile. And lastly, we can also measure the fraction of volume occupied by these cluster counterpart voids as a function of their corresponding mass scale. And for example, if you were measuring the volume fraction occupied by cluster counterpart voids corresponding to halos of 10 to the 15 h-inverse solar mass is about, for instance, this is about close to 1%, but it goes up to like 50% if you start to include smaller mass halos, for example, 10 to the 13 h-inverse solar mass. And if you compare two different measurements at different redshift, you can say that these voids are actually growing in size. So combining all these previous properties, we can conclude that these cluster counterpart voids form a unique population of voids in a sense that we can always associate these voids to their overdense counterparts. And also these form a very uniform or homogeneous population in terms of their inner mass distribution and also their average density contrast, which I didn't show here, has very universal value close to the spherical expansion model. So we have, ideally, we have a very good concept of cosmic voids in this way. But the now following task is to ask, are we able to identify these structures from a given data? And especially one has to ask, can you do it without utilizing their counterpart or like inverted universe information? And we can do it, and we can extract or retrieve these regions from density field by utilizing some free parameters, smoothing scale and density threshold and volume threshold. And I won't bore you with the technical details, but this method is based on our previous findings. And to qualitatively describe what we've done is that if you're looking for a cluster counterpart void corresponding to some mass, then you can always compute their typical mass using this relation. And then the volume under a particular density threshold can be also calculated from using that relation. And if you specify some mass ranges, then you know that the volume under this threshold will be always larger for a larger void because we're having a self-similar density profile. So for a given density cut, you will have always larger volume for a cluster counterpart void corresponding to a larger mass halo. And that is how we extract these regions from galaxy density field. And this is the final result. So again, I'm showing you the same regions in our simulation in 4 different panels. And these colors represent the mass ranges of the halos, which were used to identify cluster counterpart voids. So you can consider these colored patches as the correct answer we want to retrieve from a given density field. And the black contours are the regions we identify from density field utilizing the free parameters. And for example, if you focus on top left panel, where we are asked to identify cluster counterpart voids corresponding to halos more massive than 10 to the 15 solar mass, which is in blue. And if you compare the black contours, you can see the agreement between the 2 regions. And you can also do similar practices to different mass ranges of cluster counterpart voids, where you can still find good agreement. Now, in reality, what we are observing is not a dark matter distribution, but a galaxy distribution. So we placed mock galaxies on top of a dark matter distribution using so-called MVP galaxy correspondence model, which is basically assigning galaxies to the gravitationally most bound particle in that halo. And since our method works on density field, the galaxy density field has to closely follow the underlying dark matter density field in order to achieve reliable detection. And so I'm showing you a visual map of different types of galaxy density field, whether it's weighted by their number or by their mass. And if you look at the morphology of these density field, it looks more or less the same, except the color contrast. I'm not sure if you can see the difference between these two figures, but the color contrast is enhanced. In other words, their amplitude of the fluctuation has been boosted. And this is just simply reflecting the fact that galaxy density fields are biased tracers of the underlying matter field. So you have this fluctuation amplification. But one thing to note here is that even if the density field itself has been stretched, if this amplification is perfectly by a factor, by a constant factor, then our identification still works very well. But if you qualitatively compare density fields from dark matter density field to galaxy density field, there is some scatter around this nonlinear relation, meaning that if you have some region in dark matter density field, that is not always the lower density region in the galaxy density field. And this means the order of the density in dark matter field and the galaxy density field is not preserved. And this is due to the shot noise when you construct a density field using a discrete galaxy distribution. And there is another contribution from the intrinsic nature of bias, which is stochastic. So anyway, but we can do similar exercise. And if you quantitatively compare the recovery rates or detection rates in terms of completeness and or reliability, where completeness gives you how much fraction of the cluster counterpart voids and desired mass range is identified, whereas reliability gives you how much fraction of the identified regions corresponds to the cluster counterpart voids in desired mass range. So we tune the free parameters to have the highest balance between these two metrics. So, and now I'm showing you the detection rates in dark matter density field and galaxy density field. And as we can expect, we can achieve highest detection rates when we are dealing with a dark matter density field. But this is like about 10% decrease when you're dealing with a galaxy sample, assuming that we are using like volume limited sample from Slow and Digital Sky survey, then we can achieve like 60 to 65% of completeness or reliability. But we can improve this when we use DESI or Sphere X-like galaxy samples up to 65 to 69%. And this increase is due to increasing sampling density, which decreases the shot noise contamination in our identification. So there are some interesting sciences we can do with this cluster counterpart voids, as these cluster counterpart voids are also shown to remain in quasi-linear in their dynamics. So we can model void galaxy correlation with a linear theory, which makes us our life easier. And then we can use that to measure linear growth rate, which is a direct probe of gravity. And another avenue is to extract primordial information on smaller scale, like within voids, where we still remain in quasi-linear regime. So we can apply linear theories, and this scales usually in overdense regions are already entered in fully nonlinear regime, which means it's hard to model. So we can have like pristine access to these scales. So I will summarize my talk. So we introduced a new concept of defining cosmic voids under the so-called void cluster correspondence model. And I hope I convince you that we can actually identify them from a given dark matter or galaxy distribution in a way that those voids are always associated to certain mass scale of clusters. So I will stop here. Thank you.
Thank you. Were there any questions?
Yeah, thanks. This is really cool. So I think I understood that the way you define the void is like by finding some calibration through the simulation once the correspondence with the cluster.
Yeah.
But I guess those simulations must have made some assumptions that part of the plan might have find these catalogs of voids to test those assumptions, like the assumption about dark energy or dark matter. So with this, have you thought about doing this with different simulations that relax some of those assumptions, or like looking for new physics based on this?
When you say assumption, you're talking about different cosmological models or different cosmological
Different
parameters?
models, different parameters, different laws of gravity. Like
Yes. So that's a very good point. So actually, in this setup, we're assuming some flat lambda seeding, which is like standard concordance model. And if you want to actually find how these voids change in different cosmology, one has to run another simulation to actually follow that, because there is no like theoretical understanding how we can make it different. And yeah, that's one caveat, but I won't say this is the caveat only for us, but it also applies to all other identifications, since if you run any kind of void finders, or if you try to predict some statistics, you always have to run it or use different models. So I think that is kind of same stage or same disadvantage for every different approaches. But I think we should definitely have to run on a different cosmological model to see how they change.
So that brings up a question. If you run other void finders,
Yes.
do you get the same density profiles or the same statistics that you got, or what's the difference?
So we haven't. So I didn't myself compare it to the different void finders, but there is a literature showing how their density profile looks like when you run the most sophisticated one these days, and to this kind of analysis. Then you can also, you can actually tune to find the similar regions if you tune the parameters. But the point here is then, again, tuning meaning that there is some arbitrary decision. You have some prior idea on what kind of void you are actually looking for. So then you can choose some numbers to get those. But in our analysis, we're not trying to start from one's own decision, but we're just trying to stick to the basic physics, that all the structures are just growing from initial density fluctuation and only under gravity. Then we can just directly relate to the well-known part, which is gravitationally bound part, and then just extend to the other side. So in terms of density profile, going back to density profile, you can make it look similar. So there's no big difference, but one point in this identification I would like to mention is that you can always connect to some mass scale of halos, which I think you can, to some extent, you can increase the amount of amount of information when you do statistics using only halos. Then you can also do the similar statistics as we do a galaxy cross correlation. You can have some statistics about voids, and you can you have now some leverage to the overdense counterparts. And that is, if you just stick to our convention, then you can always double the information in that sense, because we can connect some mass halos to certain size voids. So I think, yeah, that's the key difference between these identification.
So I think Martine has a question if you would like to ask.
Sure, thanks. So I guess you kind of addressed this.
Martine, your audio is kind of weird.
Or now?
That sounds better.
Okay, probably my headphones are funky. So I was saying, you kind of started to address it in that last response, but yeah, I was wondering about some of the advantages of having voids associated with clusters in this way. And I guess it sounds like the idea is to be able to kind of extrapolate or use the predictions that we already have for halos above a certain mass, and then be able to apply those to voids as well. And like you said, kind of double the statistics. But does that only work for like basic number counts? Because I assume like 2-point functions are going to be different, even though it's the same numbers, the spacing is still going to be different, because as you talked about, the position of voids don't move as much.
Yes. So I guess in terms of 2-point correlation functions, if we approximate these halos to peaks of the density field and voids as troughs of the density field, I guess in principle in Gaussian random field you will expect very similar 2-point correlation function, because it's just a sign inverted like density extrema. So in principle, yes, you would expect a very similar 2-point correlation function, but in reality, at late time, especially if you're dealing with these halos or gravitationally bound objects, then they are, I mean, it depends on the scale where you're looking at, but it could be already entered in the like quasi or nonlinear regime. And that would, I think that would make the difference with the void correlation functions.
Okay. Yeah, it's interesting. Okay, thanks.
Okay, if there are no more questions, then let us thank our speaker once again.